Good day, viewers. You're welcome to Understanding Chemistry by Nkechi. Today's lesson we're looking at multiple equilibria, continuation equilibrium reaction and processes. Alright, look at this equation. So this is equation 1, this is equation 2. So A reacts with B to give D. So that's the equilibrium constant for equation 1. X gives E plus B. So K2 is the equilibrium constant for equation 2. So as you can see, the overall reaction is A plus X plus B will cancel out. You have A plus X to give D plus E. So in such a case, you can see that the overall reaction is the product of the equilibrium constant of equation 1 and equation 2. So this is the equilibrium constant for the overall reaction is K. So that's the product all over what? Reactant. So we're going to prove if the equilibrium reaction for the overall reaction is the product of the two equations. Okay, look at this. Equilibrium constant for K1 is concentration of D divided by concentration of A times concentration of what? B. We do this one for K2. K2 is equals to concentration of E times the concentration of B divided by concentration of what? X. Okay, look at this. So we're going to multiply K1 by K2. So K1 times K2 is equals to, what's K1? Concentration of D times concentration of A times concentration of what? B times K2 is E times that of B divided by concentration of what? X. So look at this equation. We are going to eliminate B. So B will cancel B. And you are left with K1 times K2 is equals to concentration of D times concentration of what? E divided by concentration of A times concentration of what? X, which is equals to K. That's anything that we have here. So anytime you come across multiple equilibrium, you are given equation that leads to equilibrium equation that leads to overall reaction. So the overall equilibrium constant is the product of the individual equilibrium constant. The equilibrium constant for the following reactions are as follows. You can see this equation, and the equilibrium constant K1 is 2.9 times 10 raised to the power minus 4. So equation 2, the equilibrium constant K2 is equals to 26.3. What is the equilibrium constant for the reaction, for this reaction? As you can see, this reaction is this overall reaction for the two equations. This overall reaction. Okay. So what it means that Cl2 is being eliminated. It's being eliminated. So this is the overall reaction. But if you look at this overall reaction, you can see that COCl2 gives CO. So in this case, you are seeing CO on the right hand side. While in equation 1, CO is on the product side. So what it means that we are going to rewrite equation 1. We are going to reverse it. So first step we are going to reverse equation 1. So rewrite equation 1 or reverse equation 1. Equation 1. So equation 1 is going to be CO plus Cl2 gives Cl2. So the equilibrium constant here is K1. Now we'll call it K3 for this equation. So K3, what will K3 be? K3 is going to be inverse of this, inverse of K1. So what should be the new value? The value is going to be 1 over K1 is 2.9 times 10 raised to the power minus 4. So 1 inverse of 2.9 times 10 raised to minus 4, we're going to have 4566.2. So that's the value for K3. This is not the final answer. So let's look at equation 2. In equation 2, you can see that PCl5 phosphorus 5 chloride is on the product side, but this equation, it appeared on the reactant side. In the overall reaction, it appeared on the reactant side. So we're also going to equally reverse equation 2. So, or write equation 2, rewrite equation 2. So we're going to write it. So you have PCl5 reversible reaction give PCl3 plus Cl2. So we can call this one K4. This is K4. So K4 is inverse of K2, which is equals to 1 over 26.3. K4 is equals to 0.038. So 0.038. So the question is, what is the equilibrium constant for the reaction? So as you can see, if you add this equation together, K4, and if you sum this thing, the overall reaction of this is going to match with this, what we have here. So because this Cl2 cancel Cl2, you sum it together, you have PCl5 plus CO, which matches this thing. So the overall reaction is going to be, remember we said that the overall reaction is the product of the individual equilibrium work constant for the individual reaction. Equilibrium constant for the reaction is going to be equals to K3 times K4. So what's K3? K3 is 4566.2. What's the value of K4? 0.038. 174. So anytime you come across this thing, if the other one is reversed, reverse it. Right. When gases react, the equilibrium constant may be expressed in terms of partial pressure of the gaseous reactant and gaseous product. So such equilibrium constant is called partial pressure equilibrium constant, and is denoted by Kp. So let's look at this equation. A reacts with B to give C plus D. So we're going to express this in terms of partial pressure Kp, K subscript P. So it's still the same thing. Product. So this partial pressure P for this product, capital C, or subscript, raised to power the coefficient, stoichiometric coefficient C, times the partial pressure for product D, raised to power the coefficient, which is small letter d. It's just exactly what we did before, just that we use P. So A, remember, I'm not using concentration, this square bracket concentration. Okay. So partial pressure for reactant A. Oh, sorry, this is supposed to be. So reactant A raised to the power of the coefficient, which is A, times partial pressure for reactant B raised to the power of coefficient, which is smaller than B. So C, PC, PD, PA. So this PC, PD, PA, PB. So this represents partial pressure for C, partial pressure for D, partial pressure for A, partial pressure for what? For B. We'll be looking at the equation that connects Kc and Kp. Kc and Kp. Now the question is Kp is equals to Kc times gas constant times temperature in Kelvin raised to the power of change in the number of moles. Okay, look at this. So this is equilibrium constant. This R represents gas constant. This temperature in Kelvin. This changing in the number of moles is means. So this represents this stoichiometric coefficient C plus that of D minus the one of the reactants A plus B. So if you do this, and maybe for example you're getting 2, you put raised to power 2. If you get minus 2, you put minus 2. Okay, let's look at this equation. The reaction of ammonia. So production of ammonia. The production of ammonia. N2 plus 3H2 to give ammonia. So for the partial pressure, only gases. If it's solid, if it's liquid, we're not going to express that one. It's only gaseous product and gaseous what reactant. Okay, look at this. So if I'm using this formula, Kp is equals to what? Kc RT. So what is going to be the change in the number of stoichiometric number of moles? Okay, so what's going to be the stoichiometric coefficient of the product minus of reactant? So here, product I have 2. So 2, that's product minus the reactant. How many do I have? 1. That's if it's solid, I will count it to only for gaseous rather than product. So 1 plus 3, that's 4. So 2 minus 4 is minus 2. So in this case, it should that be raised to the power minus 2. Let's look at question number 1. Kc for the ammonia synthesis reaction at 700 Kelvin was found to be 6.3 times 10 raised to the power minus 2. Calculate Kp for the reaction under the same condition. Okay, so I'm going to write the solution. I'm going to write the formula for this reaction. So let's say ammonia, nitrogen reacting with 3 moles of hydrogen. We form 2 moles of ammonia, or in gaseous state. Alright. So the formula for this equation is Kp is equals to Kc, gas constant, change in a number of moles. So this so first of all, I want to find out what the change in the number of moles is. So the product, remember, is changed. When you add the product, one of product is subtracted from what? Reactants. So what's the number of moles for the product is 2 minus for the reactants 1 plus 3, that is 4. So that's minus 2. Look at this one. This gas constant has different values depending on the unit of pressure and volume. If pressure is atmospheres and the volume is in liter or decimeter cube. If P is in atmospheres and the volume is in liter or decimeter cube, dm cube. So the gas constant they're going to use is 0.08026 liter atmospheres mole per Kelvin. But if the pressure is in Pascal, and the volume is in cubic meters. Or I can have the pressure in kilopascal, and the volume in liter. The value I'm going to use, the R I'm going to use is 8.314 joules per mole per Kelvin, 0.08026. So temperature must be in a Kelvin, absolute temperature. Even if you are giving degrees Celsius, you have to do what to do or convert it to Kelvin. So times 700. So raised to power, this minus 2. Right. So 6.3 times 10 raised to power minus 2. When you times this times 700 will give you, you'll be having 54.77 raised to power minus 2. So which is equals to 6.3 times 10 raised to the power minus 2. This thing setting as saying 1 over 5 4.77 square. So the value of Kp times 10 raised to the power minus 5. The equilibrium reaction have considered so far is a homogeneous reaction where the reactant and product are the same phase. So there are some heterogeneous reactions that eventually lead to equilibrium. For example, so look at this reaction between red hot iron and steam to give this product. So this one is solid, and this is solid, this is gas. The water is steam. So I want to say that pure solid, pure liquid don't appear in the equilibrium constant reaction. They don't appear. So their value is 1, taken as what? 1. So look at this reaction again. So chlorine gas, this one is pure liquid, this one is liquid. Remember the previous ones we considered when we were doing a multiple equilibrium. So this one, the part of this phosphorus 5 chloride is gas. So this one is liquid, pure liquid. So their unit is going to be what? 1. Okay, let's find the equilibrium constant for this reaction. Alright. So look at this. The value of a pure liquid and gas is taken to be what? 1. So this one is going to be 1. It's like saying 1 times concentration of hydrogen gas, 1 times the one of a steam. So the equilibrium constant for this is going to be. So this one is not going to appear. So it's going to be H2 is to the power 4 and steam is to the power 4. So this is the equilibrium constant for this reaction. So what is if it's solid don't appear, liquid, pure liquid they don't appear in what? In the equilibrium constant reaction. Then you can do the same for this one. So for this second equation, this one is gas, this one is pure liquid, this one is liquid. So the value is going to be taken as what? 1. So the only thing I will apply there is chlorine gas. So this one is 1, this one is 1, it's 1. So in case you come across something like this, heterogeneous reaction that eventually leads to equilibrium, the solid don't have to be there. If you put it there, it is wrong. Nickel tetraoxide when exposed to the atmosphere, absorbs water vapor according to the equation below. So this equation below So that's it. This one is solid, this is gas, and this is solid. So if the temperature is 25 degrees Celsius and the vapor pressure of water is 3.17 kilopascal at this temperature, calculate Kp. So to calculate Kc for the reaction. So we're going to put down equation for the reaction. So Kp, this solid, remember, it's always the concentration of product all over that of what? Reactant. So in this case, this product is solid, and the value for pure solid and the pure liquid is 1. So it's now be 1 over. I will not use this one because this is solid. So this is gas. Alright, so raised to the power 6. So 1 over, what's the value for the pressure of water vapor? So the vapor pressure of water is 3.17 kilopascal. So that's the 3.17 raised to the power 6. So this value is going to, Kp is going to be 9.85 times 10 raised to the power minus 4. So question number 2. Kp is equals to Kc times RT raised to the power change in the number of moles. So what's the number of moles here? Change in stoichiometric coefficient. The product is solid, so it means that it's going to 0 minus the reactant side. They have 6 moles of water vapor. The other one is solid, NiSO for solid, we will not use it. So 0 minus 6, not 1 minus 6, because that product is solid. So it counts as 0. Nothing is there. It means that I'm not using anything there, that's 0. Minus 6 equals to minus 6. Temperature must be in what? Kelvin. So we are given 25 degrees Celsius. You add plus 273. So it will be what? 298 Kelvin. So that value, we are looking for Kc. So the value for Kp is 9.85 times 10 raised to the power minus 4 equals to Kc. So this gas constant I'm going to be using, since the pressure is given in kilopascal, we'll be using 8.314. 8.314. If you're not giving any value, like the first one I did, the first question, you're not giving any, the pressure. So in that case, use 0.08026. But the pressure is given in kilopascal or pascal or Newton meter square. Please use 8.314. So our pressure is 8.314 times. So the temperature we'll have here, temperature is 298. So what's the change in stoichiometric coefficient is minus 6. So 9.85 times 10 raised to the power minus 4 is equals to Kc. So this times this, 9.85 times 10 raised to the power minus 4 is equals to Kc. So if you want to remove this inverse, it will now be times 1 over 2477.6 raised to the power 6. So of case equals 2.28 times 10 raised to the power 17. Alright, thank you viewers for watching. If you're not subscribed to my channel, subscribe, like, and comment. Thank you for watching. Do have a great day. Bye.